All right. Hello, everybody, and thank you for coming here to this new session of the Machine Learning Coffee Seminar, or lunch seminar today. And we are incredibly lucky to have here with us Jakob Macke, who is a professor of machine learning science at the University of Tübingen. He's going to talk about simulation-based inference and the place it takes us. And we are very excited to hear what he's going to talk about. So I will just give you the scene and then you can proceed. Thanks, Jakob.
Great. Thank you for the invitation. Two remarks before I start. The first one is I'm obviously sitting here in Tübingen in this virtual seminar, and it's a bright and sunny day here, but there's this one spot in my office which I can't cover by shade. So I will have to awkwardly move around to avoid that. So if you see that, I apologize for that. And the second one, as I mentioned to Ludi earlier, I made a presentation which gives us where I talk about a few different applications, and I very much would invite people to interrupt me and discuss. And if I don't get to the end of what I wanted to say, then this is not a problem at all. There's no punchline waiting at the end. So I'd much rather be interrupted and have discussion than give my whole presentation. Do feel invited to interrupt me and ask critical questions. So the title of my talk is Simulation-Based Inference and the Place It Takes Us. And I want to start by kind of giving a motivation of how I ended up working with simulation-based inference. So as some of you might know, I'm half a machine learning person, half a computational neuroscientist. And in computational neuroscience, we often are faced with different types of data, and we want to build models that can explain that data. For example, we might have some voltage recording, and we might want to fit a Hodgson-Huxley model to do it to explain how that single cell will respond to an external stimulus. Or we might have some population recording, so neural activity for many neurons, and we might want to build a population model, for example, an excitatory inhibitory pool model, which is wired together such that we can qualitatively or quantitatively explain that data. Or we might have some psychophysical data where an animal or person is given a task, and the difficulty of that task can be varied by changing some stimulus strength or some task difficulty parameter. And then there's classical cognitive models such as drift diffusion models that we want to fit to that data. So all of these scenarios share this common structure that we're given some data, and we want to fit some mechanistic model to it. And by mechanistic model, I mean models that are designed by neuroscientists or some domain scientists thinking about what is the right interpretable model. These are models that are not designed with statistical convenience in mind, but with interpretability. And in fact, often we don't actually want to fit the whole data. And obviously these mechanistic models, they will have some parameters that we don't. And often we or the people applying these tools, they don't care about fitting all the data, but they often have some properties of the data that they care about in particular. For example, for psychophysical data, they might want to say, well, we really care about whether the response is correct and what the reaction time is. So out of the possibly multidimensional response, there's some aspects of that they care about, and they can be quantified by using summary statistics on the data. So these different scenarios are all obviously statistical inference scenarios, but one thing that frustrated me in my time or in my half-life as a computational neuroscientist is that the kind of statistical models we use, at least in neuroscience, generalized linear models, recurrent neural network models, maximum entropy models, they can all efficiently be fit to data, but they often don't have this mechanistic interpretable flavor. In contrast, there's lots of mechanistic interpretable models in neuroscience, Hodgson-Huxley model, multi-compartment models, balanced network models, drift diffusion models for decision-making that are highly interpretable, but they're hardly ever used or rarely used for data analysis because we can't fit them to data. So my primary motivation for working on these problems has been that we really want to combine the interpretability of mechanistic models with the efficiency with which we can fit statistical models to data. So what we want to do in my group is to try to combine, kind of get the best of these both worlds. And one concrete question that we focused on quite a bit in the last couple of years is to think about how can we do Bayesian inference efficiently for any mechanistic model, including ones that are specified as simulators. So the ingredients of any such approach would be that we have a forward model, the mechanistic model, and that allows us sorry, maybe we start with the data. We start off by having some data, which in neuroscience could be, for example, fluorescence traces, and I will refer to the data as x0. We have some model, a mechanistic model that we can use to generate data given some parameters. And in the Bayesian sense, we have a prior over parameters that tells us the parameter ranges that a priori are plausible with the data. And given all these ingredients, all we want to do is Bayesian inference. So we want to calculate the posterior distribution. And I've colored in here a bimodal posterior, because one thing that I think is, I mean, it's often in many cases, but particularly important in neuroscience, is that we often work with models that are only loosely constrained by data. So getting a point estimate of the model is often not sufficient, but we really want to have tools to find possibly complicated posterior shapes, including multimodal posteriors. So both to estimate them and also then to explore them visually. So for us, having the ability to estimate flexibly shaped posteriors is very important. We all know how to do Bayesian inference. So the posterior distribution is just proportional to the product of the likelihood and the prior. But we all know that there's many devils hidden in the details. And one particular difficult thing is, as I mentioned before, is that these likelihood terms can often not be readily computed. And this has given rise to this term of likelihood for inference, which I personally never really liked. And that has to do with the fact that all these models do have likelihoods. So from a mathematical perspective, they have likelihoods. And in fact, often we could compute them if we went through a lot of work. So either, and if, for example, one reason why it's often hard to compute these likelihoods is because the forward models are implemented in some software tool, for example, the neuron simulator, often when you work with single cell models, that just doesn't give you access to the internal workings. So it's not a mathematical question of this being likelihood free. It's more that it would be a nuisance or very expensive to estimate the likelihoods. So the term that I prefer over likelihood for inference is simulation-based inference, because it doesn't make a strong statement about whether the likelihood is available or not. It just says for us, it seems more convenient and possibly faster to use simulations rather than likelihood evaluations. But mathematically, there are likelihoods underneath, and often with some extra work or a lot of extra work, we could even evaluate. So we've thought about different simulation-based inference methods, in particular with a focus on neuroscience. And the one that we've probably spent most time on is a class of methods called neuropositive estimation. And this is primarily work by a former graduate student of mine, Jan Matthias Lückmann, and two postdocs, Pedro Gonçalves and David Greenberg, that have worked on these questions in my group. And the basic idea to try to convey this graphically is that for neuropositive estimation, we start by randomly sampling parameters from the prior. And then for each parameter set we sample from the prior, we can generate some simulated data. And that gives us a database of parameters and data generated from those parameters. And then we can either use the data directly or put summary statistics on it, but it gives us a supervised learning problem involving parameters and data. And then we can fit a density estimator, a conditional density estimator on the data. So it's data that puts in some, it's an density estimator where the input is some data X and the output is a distribution over theta. So it's a supervised learning problem where we put in the data and say, what's the parameters that generated it? And in fact, what's the distribution of parameters that could have generated it? So conditional density estimator where the input is data and the output is a distribution over parameters. And the density estimator in itself will also have parameters that we here denote as phi. And so one thing that plays a crucial role in all of these approaches is the availability of flexible density estimators. And what we use, I will not talk about it in more detail, but the density estimators that we use primarily and that we have very, I think, very positive experience with are normalizing flows. And the basic idea of a normalizing flow is that we want to have a way to generate complicated distributions from simple ones. So the recipe is to take a Gaussian distribution, push it through a neural network to get any shape we want to have, and we can make the neural network dependent on a covariant X, giving rise to a conditional density estimator. there's obviously the need for us to evaluate the change of variable formulas. So we cannot use any neural network, but there's been many different flows, which basically are different network architectures that allow us to compute these change of variables efficiently. So the ingredient that we need is a conditional density estimator, and we train that purely on simulated data. And once we've trained it on simulated data, we can plug in the real data and get a distribution, a conditional distribution over parameters given some real data x naught. And if we do everything correctly, then one can show that this conditional density estimator evaluated the data provides an approximation to the true posterior distribution. And what's really cool here, from my perspective, is that this conditional density estimator is purely trained on simulated data using supervised learning, but it gives us access to the posterior distribution without us ever having to evaluate the likelihood, or in fact, ever having to explicitly evaluate Bayesian. And this is just a sort of a flexible and powerful way to generate, to do Bayesian inference. It does have disadvantages. The one disadvantage that it has is that obviously it's inefficient in the sense that we generate random models from the prior, which means we might generate many models that look very different to the real data, so we immediately discard them or that they don't provide useful information. But there are various ways to close the loop that we say once we have an initial estimate of the posterior distribution, we can use that to adaptively generate additional data, such that next generations of data we generate are more and more look more and more like the real data. And one can use either active learning to get a better handle on what simulations to take, or a simple heuristic is just to take the current estimate of the posterior as the proposal distribution for the next round of this approach. So this basic approach is one that we've coined sequential neuroposterior estimation, because we sequentially use neurodensity estimator to estimate posterior distributions. But the basic idea of this is obviously much older. I mean, to start with, it's really, one can think of this as a special case or a modern version of regression adjustment methods in approximate Bayesian computation that have been around for probably 20 years. And the modern version of this was suggested by George Papamakaris and Ian Murray in a Neuroscience paper in 2016. What my group has been doing since is to think about more efficient ways to implement this approach. And this often boils down really to the question of how we adaptively generate simulations at this step. Because this is really this adaptive step here is the one where different methods really deviate from each other. And we've had sort of two versions of improved update steps, as well as different applications papers of this in Neuroscience. Obviously, this is not the only approach to do Bayesian inference on simulated data. One approach that we've started to explore recently has been to think about how we can basically marry adversarial learning with simulation-based inference. And in part, this has been prompted by many questions saying, well, simulation-based inference and adversarial learning, they seem kind of similar. And they are similar, but they're crucially different. But one can use adversarial learning as a way, basically to plug that into neuroposterior estimation. And the basic idea is the following. One can use adversarial learning or adversarial inference to estimate distributions or ratios of distributions. And one can apply this in a manner that basically, rather than explicitly estimating the distribution using a flow, one can use adversarial inference to get an implicit estimate of the distribution. And the basic idea is, again, one starts with a prior, and one generates simulations from that prior. And that gives one access to the to basically the joint distribution over parameters and generate the data. And then one can take use again to generate simulated data. To simulate parameters and use a discriminative loss to check whether the approximate posterior one gets is the same as the true posterior one would want to have. So one has a generator that samples parameters from the approximate posterior, and one that has a discriminator that discriminates implicitly between the approximate posterior and the true posterior. And this gives one an approach that's conceptually similar to neuroposterior estimation, but rather than using the neural density estimator, one uses this setup of a discriminator and the generator. So you might ask the question of, like, why should I use this if I can just use the other approach that I suggested before? And to be honest, we don't have a good answer on when to use what. What we do know is that GANs can be very powerful on very high dimensional problems, and we have got some demonstration of that in the paper. But it's also true, and we've certainly experienced this, that training GANs can be very painful, and they have many hyperparameters. So this is likely not the model of choice if you just want to have a GAN, as if you just want to do simulation-based inference on a problem and want to get it run quickly. So this is we've done this study both to really understand how these two approaches connect to each other, as well as to have a way to use GANs in applications where they are promising. But this will not be your go-to tool for like a small simulation-based inference problem, because then you would still have to deal with all the hyperparameters that a GAN has. So one alternative to neural posterior estimation would be this adversarial approach. Another approach would be to say, well, rather than estimating the posterior distribution with a density estimator, we can just estimate the likelihood with a density estimator. And in fact, this has been coined sequential neural likelihood, and it can be thought as a modern version of synthetic likelihood approaches. So rather than training your density estimator on the posterior, you train it on the likelihood. And this has one big advantage, and that you don't have to sample from the prior at all, right? As I explained earlier, when you want to do posterior estimation, you have to sample from the prior, and there are the possibilities to do this adaptive loop as I drew it in, but one has to be very careful on this adaptive loop to make sure that one still does valid basic inference. If you do neural likelihood estimation, you can just sample whatever data you want to have, because it really doesn't matter the distribution comes from. So you have full flexibility to sample from any distribution that you want to. The downside is that it only gives you an estimate of the likelihood, but typically you really want the posterior. So you have to do something else. And the something else in the past has been to do MCMC sampling, and that is fully flexible. But the downside of it, that it is slow. And this is particularly a problem here, because when we have these multi-round approaches, where we often change our things and really want to re-estimate very often, we would have to run MCMC many times. So it's not a case of having to do MCMC once, but if you have like 10 rounds of simulations, you have to do MCMC 10 times or 100 times. So this is really, you're paying a big price for the slowness of MCMC here. So the kind of obvious solution is to try to do something that's faster than MCMC, although possibly not as flexible. And the obvious solution would be to do variation. So this is really so the study that Manuel Glöckler, right, student in the group now, in some ways is really take two things that existed individually and plug them together. And what he showed in his ICLR paper is that this can work quite well. But so he actually had to not only plug them together, but to think really carefully about what variation inference method you want to use. And in particular, if you take an approach that is mode seeking, so you just take the classical variation inference based on the Keller diversions, he empirically found that this does not work very well, because often you overcommit to an S. So in these multi-round schemes, this often led to overcommitting to a single mode of the posterior and then never exploring the other ones. So the approach itself is simple. You just take neural likelihood estimation, combine it with a variation inference. But to get this to work in practice, it's really important to take the right variation approach. So this concludes my somewhat rushed approach to different simulation-based inference methods. And for the rest of the talk, I will just talk about different applications in neuroscience and other application domains. But maybe this is a good point to briefly pause and ask whether anyone has any questions.
Any question for the public? I mean, otherwise, I have some. So yeah, okay. So this is all. Yes. So you covered some of it already before, essentially. Yeah, when you were talking. So what would be the advantages? So one thing that says yes, essentially, how hard is it to train these models? It's not begun, let's say, by the standard other. So how do you choose the architecture? How do you decide whether you found a good solution? Say, is there a risk of overfitting? All these kind of questions you get from standard, let's say, neural network training.
Yeah, I think partially I can. So we don't have a one-size-fits-all answer. So this is something that I personally find very unsatisfying at the moment. But one thing we're trying to do is just to collect practical experience and turn that practical experience into some kind of heuristic guidelines. And the two things we've done in that direction is that we've published a toolbox where we try to have this usable by others, and that also allows us to kind of update default choices. What we found is that for small problems, let's say 10-dimensional or less, then these approaches can be remarkably robust to the choice of architecture. So that if you take a neural network that's not too deep and can be pretty shallow, then often this works pretty much out of the box. When you go to more challenging applications, it really becomes a question of tuning the network and thinking hard about what network architecture to use. So we don't have a full understanding, or we don't have automated guidelines of what network architecture to use when. The second part of your question, which I think is very important, is, so how do you know whether this worked, right? Because you can, on toy cases, you can check the correct answer, but in practice, you will not know what the correct answer is. And one thing that's really important in that respect is to have some diagnostics or heuristics that allow you to check when things are going wrong. And I don't have a slide on this, but what we found most useful in practice is to just have posterior predictive checks. And so you fit your model to data, then you simulate from it, and you find whether you recover the data that you started off with. And if one wants to do this systematically, that gives rise to, for example, simulation-based calibration techniques where you say, if I do posterior predictive checks many times, then on average, I should, or basically in the marginal, I should recover the prior over parameters. And these kind of checks are, I think, both very important. We try to build them into the toolbox so that it's easy for people to do them. But all of these checks typically give you, they can't prove that it worked, but they can warn you when it's clear that it did not work. Yeah, but I think this question of checking whether things worked and identifying when it didn't work is crucially important. Just because I mentioned it here, so we have this toolbox, and we also have, and when I say we, this is particularly Jakob Macke's work. He made this website where he basically implemented a range of different standard tasks in the literature and a number of different metrics for evaluating them. And he used cases where you can have access to ground truth posteriors. So where you can, where there's some MCMC sample or some other approach where we trust that this posterior is correct, or sometimes even done by numerical integration. And that on this website, one can basically upload either a new algorithm, or one can upload a new algorithm and then basically compare it to many others as a function of simulation budget. And this is, for example, a Tübingen task that someone proposed, and you can just compare a range of different algorithms and see, using a metric, in this case, the C2C metric, which of those algorithms works better on that task. And he did this quite extensively. And what we found is that, I mean, there's a few things we learned from this. And the first one is, somewhat frustratingly, depending on the task, it seems always another algorithm that works best. So we couldn't say, like, this, from the methods we tried, this is like the one algorithm to use. And the second thing that we also found is that, at least to me, it was surprising how big a gap there is between perfect performance in most of these algorithms, even on relatively simple tasks. So even for relatively low dimensional tasks. So it's not, this does not seem like a saturated problem, but it does seem that there is room for improvement. One criticism of this approach is that obviously the it could always be that just it was our implementations of these algorithms that are the problem, not the algorithm itself. And that's inherent whenever you take someone else's algorithm, that you can do your best case of tuning it. But in some ways, how hard you have to work to tune it also gives you some indication of how robust the algorithm is. But this is why Matt has actually spent a lot of work to set this up in a way that other people could contribute the algorithms, such that one can really see how well different algorithms. And I just sort of want to issue this invitation that if someone has an algorithm that could work on one of these tasks, then they should please upload them, so then one can basically put them to the test. A final thing that's in this paper, and it's somewhat hidden in the paper, but there's also this page where we try to collect our practical experiences and basically say, based on the experiences that we have so far, this will be our recommendations for how to pick an algorithm on a given problem. It's likely hidden a little bit in the paper, but this is our best guess on how one should in practice approach simulation-based inference problems.
Cool. Yeah, this is really fantastic. Yeah, thanks a lot for the answer. And I actually have another question, if you can fit it now. So, I mean, I was wondering, I mean, this is my kind of a bit speculative, but let's say if there is any, so because the kind of approaches you're using now are, so they're not, you're not building Bayesian neural networks, right? You're building standard neural networks that recover Bayesian posteriors. So have you tried, or say, of combining this with Bayesian deep learning to to have actual uncertainty about your estimates?
This is an excellent question. So we are Bayesian in the general approach, but the density estimate we fit using a point estimate. And in the past, we've had two papers where we also tried to be Bayesian about that. So basically double Bayesian. And this was both, and in fact, in both of Jan Mattis's neuroposterior estimation paper, where we tried to do variational inference on the density estimator, and also in Jan Mattis's synthetic likelihood paper, where he tried to use ensemble methods to get uncertainties over the parameters. And our experiences so far were mixed in the sense that being Bayesian about it did not lead clear advantages in terms of performance in the end. So we could not construct a very clear case that's saying if you do the more expensive Bayesian method, you get a much better estimate of the posterior than if you just do a point estimate on the density estimator. My hunch is still, I mean, this is one of those cases where where this is just empirical results. But I would very much like to not give up on these points and still see whether being Bayesian about the density estimation also helps the estimate of the posterior distribution in the end. And there are a few cases where it's plausible that it might help. And this is particularly in the initial phases of learning. So when you start off trying to get some estimate from your first couple of simulations, you're really in a very data poor regime. And then it seems plausible that being Bayesian and having priors and having uncertainty will help you in that regime, but we've just not empirically found strong demonstrations. But it's definitely something that I do not find satisfying.
Yeah, cool. And just as a sort of quick follow-up, when you were doing this, when you tried this in the past, were you doing active learning or say non-active learning with the Bayesian?
So when we were Bayesian on neuroposterior estimation, we did not do active learning. When we were Bayesian on likelihood estimation, we used active learning. And in fact, there we used the uncertainty in the acquisition function. But we were sort of half Bayesian in that we used ensembles. And we did not evaluate carefully whether that ensemble is really corresponds to a Bayesian ensemble or just some sort of heuristic uncertainties.
Okay. Yeah, because I'm asking because I could imagine that essentially maybe to exploit Bayesian, active learning would help a bit, but that's would be my intuition.
But I think this is a good. There's room for more work in this area.
Okay. Thanks. I think I would like to continue with the talk now. So, thanks a lot.
In the interest of time, I will actually skip this example here, which is an example in neuroscience where we applied this to a method to a famous model in neuroscience from the stomatogastric ganglion, which is a model that is very famously published, studied in neuroscience in particular because it has this strange parameter landscapes, and we used simulation-based inference to explore these. I will skip this in part because I've spoken about this in the past, and if someone is really interested, they can either find the paper or find a YouTube video on it. So I will skip to another example. And this other example is one which in part motivates this, the title that I chose, simulation-based inference and the place it takes us, because as I mentioned, we really started off working on these questions by a motivation from neuroscience. But then in particular in Tübingen, we have this cluster machine learning and science, and we interact with a lot of other scientists. And out of that grew a collaboration with with our neighbors, the Max Planck Institute for Intelligent Systems, in particular Werner Schurkoff's group, who have a collaboration with the Max Planck Institute in Potsdam on doing inference on gravitational wave data. So this here is a simulation of two black holes that merged, I think 1.3 million years ago. And then this merger of these two black holes sent these very fine ripples through space-times called gravitational waves. And these gravitational waves can be detected using extremely sensitive detectors. And what astrophysicists try to do is to try to reconstruct from these detected waveforms some properties of the underlying black hole mergers. Where on sky were they? What were the masses of the two black holes? What were the spins? So you have some data. In this case, this would be the so-called strains of gravitational waves that are detected in different detectors. This, in particular, these are two classical black holes. This is a very classical event here. And so from this data, you want to infer the underlying parameters. And they have excellent forward models. Relativity theory gives you a forward model of how, given the parameters, you can predict the data. But in practice, you want to go from the data to the underlying parameters. So this is a classical problem, and they've investigated extensively very powerful MCMC samplers for solving this inference problem. What we thought about is whether using simulation-based inference, one could do this more efficiently and possibly more accurately. And this is, as I mentioned, a collaboration with Werner Schurkoff's group and Alessandro Buonanno's group, and was carried out by Max Stacks, a graduate student of Bernhardt, and Stephen Green, a postdoc in Potsdam. So we use simulation-based inference to go from these gravitational wave models to a posterior distribution over these parameters. And one thing that Max and Stephen developed is a variant of simulation-based inference, of neuroposterior estimation, that Max called DINGO. And I just want to quickly run this. So what's really cool about DINGO is that it can solve these posterior estimation problems very quickly. This is a video, but it's basically in real time. And it shows how our posterior estimate converges to the posterior estimate that you get using MCMC. In reality, the full posterior distribution is 14-dimensional. I'm just showing 3 dimensions here, but one can see that it converges basically within a few seconds. And this ground truth posterior, which is the blue line here, that's now being covered more and more by the orange line as the orange line moves towards it. This ground truth posterior obtained using MCMC takes several hours or even several days to be computed. So this puts us in a position where there's a task that took multiple hours or multiple days to compute, we can now do within seconds. And this is exciting for 2 reasons. The first one is that given that more and more of these detectors are being built, the number of events that are detected by them every year is likely to be going up a lot in the next couple of years. And that means there's a bigger and bigger strain on using analysis techniques that take multiple days to converge. And secondly, when one of these events are detected, there are also possibilities for the physicists to basically take additional measurements. But if you only find out a couple of days later where you want to measure and what you want to measure, then that window is closed. So there's kind of new applications one can pursue if one has a fast way to solve these inference problems. So we're very happy that using an extension of techniques that we started off working on in neuroscience on the scale of basically micrometers or millimeters can also be applied to models that are on the complete other end of the spectrum, basically on on the scale of on cosmological scales. And as I mentioned before, this approach called Dingo takes a few seconds to converge, whereas in contrast, the classical MCMC method used so far take hours or even days. And this is also...
Sorry, just there is a clarification question. Yes. So Umberto was asking if you obtained MCMC. I think I said you answered in talk and said yes. So you ran MCMC for a few days, but of several hours, and yeah.
And when I say and the standard MCMC actually in this case is they have, I mean, standard MCMC are kind of specialized toolboxes made for this problem. Okay, so this is there's a few different ones of those, and in fact, because these big LIGO consortia, they often have very tight rules on what method used when. So they have some tools that are basically production ready, and there's some tools that basically have passed these tests and are used in the community, and we use those tools. In fact, there's one tool we use, Bilby, and after a while we got frustrated because we couldn't get the same result as Bilby. And when we looked closer, we found that actually there was some approximations that Bilby did that our result overshot what we thought was the ground truth. And then we switched to a different algorithm called LAL inference. So there are different tools, but in the end we chose one that's not the fastest, but one where we were confident this gives us a kind of accurate results. But the algorithm we used here is neuropositive estimation, but with a twist. And the twist is the following. One thing we realized in this problem is that we got much better results if we use the geometrical structure of the simulator. So this is, on the one hand, it's a black box simulator. It's some complicated piece of code generating these synthetic gravitational waves. But from physics, we know that it obeys some geometrical properties. And one of the parameters, or some part of the parameters, is just the sky position of where, in angles, where that signal is detected. And then there's this triangulation that basically the signal is detected at different parts on the globe. And obviously, depending on where in the sky it is detected, that will change the relative timing of when it arrives in the different detectors. Okay? But that also means that there's a very clear structure you can exploit. You don't have to exploit every possible sky position, but you can just simulate in one sky position and then shift the timings along relative to where it was detected. So there's some clear structure that you know about, and you want to tell your network that this is there. But it's not actually completely kind of equivariant under those conditions, because if you shift the sky position, then also basically the magnitude of the signal will suddenly be influenced by the incidence angle. So it's mostly equivariant, but it's not exactly equivariant. It is exactly equivariant under complete time shifts. If you get the same data 1 second later, it's exactly the same signal, just shifted by 1 second. So there's both exact equivariances as well as approximate equivariance that we want to build into. So one thing that Max and Stephen came up with is a very cool way to do this, and basically involves a form of Gibbs sampling. That we say we condition on some of these parameters. So we basically condition on a given pose, on a given sky position, and simulate for that sky position. And then we can train the neural network and based on that update the sky position, and then make the next estimate based on the new sky position. So there's sort of this iteration between estimating where the signal is, and given that we know where the signal is, we then estimate the rest of the parameters. And this is a flexible way to incorporate equivariances. And the cool thing the thing that I really like about it is that it also works when it's only approximate. So we're not forcing the signal to be exactly obeying the structure. The algorithm just becomes more efficient the closer we are to that geometry. And this is, I think, a nice middle ground between exploiting prior knowledge, but not trusting that this prior knowledge is true up to the last position. And for the results that I showed earlier, this was absolutely critical to work. Otherwise, you would not get this, this performance out. And in fact, this plot that I showed earlier, these different iterations are different iterations of the skip sampler. The skip sampler is very fast because in both of the two steps, you just evaluate the neural network once. But this is why this takes 14 forward passes to the neural network, not just a single forward pass. So this is still very similar to neuropositive estimation, but has this variant where you try to different, where you basically try to do this multiple times for this to work. And with that, I think I'm basically out of time. I will skip the last part where we use similar approaches also for, again, a very different problem using computational imaging, where you can basically set up a mechanistic model of a microscope and then do Bayesian inference to do source reconstruction. And when one does this, this actually works better than all the other source reconstruction algorithms for this particular data type that we work with, but I will skip that now. And I will finish here, and I just want to hope that hopefully I managed to share how these kind of methods can be useful both in neuroscience and beyond. But I also want to be clear, and hopefully this became apparent when I talked about it, that there's many areas of this where there's still substantial room for improvement. And this has to do both with the accuracy of these approaches, as well as with simulation efficiency. And I think finally, it also has to do a lot with how usable they are for the end user. We built some toolboxes to hopefully make this a little bit easier. And I know other people have also built other toolboxes. But I think for us as a field, we need to get to a scenario where this becomes as easily usable as possible so that a wide range of users can use them. And I think the field is making progress in this direction, but I think at the same time, there's still a lot of work to be done to make these very user-friendly. With that, I want to thank our funding sources and collaborators in the lab, and put in a quick advertisement that we have an open postdoc and a scientific programmer position to work on simulation-based inference for computational imaging. Thank you very much.
Thanks, Jakob. Yeah, fantastic talk. Yeah, we don't have a lot of time, so I'll just move to the question. Umberto, I think you had a question.
Oh, yeah, thanks. Thanks to Professor Macke for a great talk, as usual. Yeah, basically, I would like to, when I saw that animation about this, what was that, gravitational waves, and the rapidity in real time of the inference, posterior inference, I almost fainted. I mean, that was quite impressive. So what I wonder is, if we consider, let's say, non-amortized inference, when we use, let's say, standard ABC tools, there are a number of things that we are aware. When I say standard ABC, I mean, the usual construction of summary statistics and comparison between observed summaries and simulated summaries through a threshold delta and so on. There are a number of theoretical results that we are aware about on convergence rates, and there's also work by Paul Farnade and colleagues. So, but it feels like this kind of normalizing flows-based approaches, they're just way more modern and honestly very competitive, especially with larger dimensional targets. So what I wonder is, how many things we don't know instead about the properties of these super efficient approaches in terms of theoretical guarantees, because it almost feels like standard ABC is just way too old and not competitive anymore in terms of computational ability to return results in decent time. So I would like to know your take on this.
Yeah, I think this is an excellent point. In the sense, we have these classical ABC methods, which have a lot of, and where we basically, the theoretical properties of them in terms of convergence, bias, etc., are relatively well understood. And we have these neural network-based approaches, which empirically seem to be, at least in some cases, much more efficient. Not in all cases, but in some cases. But we don't have this wealth of theoretical background on understanding when they fail and how they fail. So which one of the two should we, like, how should we go about this? And I both share the excitement about these modern approaches, but I also share the uneasiness about that we seem not to understand some of the theoretical underpinnings of when it will work and when it will fail. And I don't have to be honest, I don't have a good answer other than that. I think it will depend, right? And one will have to make a choice to use a tool where we understand the theoretical properties, but are willing to possibly sacrifice some performance, or we will have to a tool that gives us results very quickly, but we don't have these properties. And I think there are a few pain points here. And one pain point is that for ABC, it's well understood, but we also know that there are approximations we make, for example, in the construction of the summary statistics, right? So often ABC also, we will have to take sacrifices on terms of the accuracy we can achieve. And the second point there is that for MCMC, while we understand MCMC, I think in principle, I think for a given MCMC algorithm, to have confidence that it gives us the right answer is also difficult in itself. So I'm sometimes not sure whether I should trust an MCMC algorithm more, or on whether it has mixed correctly, or whether I should trust my neural network more, in the sense that we don't have full faith in some ways in either. And I think, I mean, to be honest, I don't have a good answer on how to proceed in that. I think we need to think about this hard so that we can come up with better answers.
Thanks.
Maybe one very last question from the chat. Joshua is asking, how is performance affected when the forward model is stochastic rather than deterministic?
Okay, so one thing I possibly wasn't clear about is that we always think about stochastic forward models, although we sometimes have forward models where the amount of stochasticity is relatively mild. And in part, I think about stochastic forward models because it's very hard to think about Bayesian inference with deterministic forward models, in the sense that it gives you kind of, if your forward model is completely deterministic, it would give you these either ill-defined or very funky shaped posterior distributions. So we always think of stochastic forward models. Everything I showed you has some element of stochasticity, but how much stochasticity is in there will depend a little bit on the problem. What is true, though, maybe, I mean, this wasn't the question, but I can point it out here, is that for this gravitation and wave model, is we would actually be able to compute the likelihoods. So one could ask the question of whether likelihood-based amortized inference would perform better or worse. The way we trained the network, it actually turned out to be easier to not use the likelihoods, although we did actually have the likelihoods. So here, the simulation-based approach, at least when we used it, this amortized simulation-based approach was more efficient than using a likelihood-based MCMC approach. But everything I showed used stochastic models.
Thanks. I think we're over time, and so we can let you go. But this was a fantastic talk, and thanks again. It's been great to have you here, and it's also great, to continue the conversation. There are many interested people here at FKI interested in the work you're doing, and so that's enough for today. Thanks again, Jakob. It's been fantastic to have you here. Have a great day, and thanks everybody.
Thank you, everyone. Thanks.
Thank you.
Bye.
Bye.